Hello, Cowboys and Cowgirls. This is Dr. Johnson. I am one of the AP Stats teachers at Capel High School, and I want to welcome you to today's presentation on the binomial distribution. We're going to continue the discussion about the binomial distribution that we started last class period. Today I want to talk to you about the expected value of a binomial distribution, the mean of the binomial distribution, and we're going to use the problem that we had before. Suppose a basketball player has the ability to make 55% of her free throws. What is the average number of free throws made in 20 attempts? Now we're going to assume that all outcomes are independent. So first of all, we have to check to make sure the conditions for the binomial distribution have been met. And we said that before that the conditions, we're going to use the BINS acronym for the first question. B stands for binary. Are there only two possible outcomes? Independent, are the trials independent? Number of successes, is the number of successes fixed in advance? And is the probability of success P a constant? Well, we do pass all of those conditions. Here I'm defining my variable X as the number of shots made in 5 attempts. And for a complete answer in this on binomial distribution problems, you need to define your variable. I've defined X as the number of shots made in 5 attempts. Binary, yes, you either make the basket or you miss it. Those are the only two outcomes. We get to assume that our trials are independent, so we pass the independence trials condition. Number of trials is fixed at 20, and the probability of success remains constant at 0.55. So we've satisfied the conditions, and we say that X follows a binomial distribution with parameters n equals 20 and p equals 0.55. Now, since it passes those conditions, we can calculate the mean or the average. In a binomial distribution X with n trials and probability of success p, the average distribution is given by this formula. The mean is equal to n times p, the number of trials times the probability of success. And the standard deviation is given by that formula in the bottom here. Standard deviation of X is equal to the square root of n times p times 1 minus p. Now you don't have to memorize these formulas. These formulas are on the formula sheet. Turning back to our problem, suppose a basketball player has the ability to make 55% of her free throws. What is the average number of free throws made in 20 attempts? Here it is. We're going to plug our numbers into our formula. The average or mean free throws in 20 attempts is 11. And I have to say, this formula should make sense to you if her chances of making a basket are 55%. And she takes 20 baskets, well, then you'd expect her to make 55% of those 20 baskets, or in this case, 11 baskets. Now, how do we interpret this mean? And I have to tell you, you need to pay attention to this interpretation because we do ask you to interpret these means. Here is our interpretation. In many randomly selected sets of 20 attempts to make free throws, we would expect approximately 11 attempts in each set would be successful on average. All of the underlined words are critical to this interpretation and part of the grading rubric. We're going to take many randomly selected sets of 20 attempts, and we expect, because this is the average, we expect approximately 11 attempts, and each success would be 11 attempts in each set would be successful on average. What is the standard deviation of successful free throws in 20 attempts? I plug my numbers into the formula. The standard deviation of X is equal to 20 times the probability of success, 0.55, times the probability of failure, all under the square root symbol, and that comes to 2.2. And of course, we're going to ask you to interpret that number. Here is the interpretation. In many randomly selected sets of 20 attempts to make free throws, we would expect that the number of successful free throws will typically vary by about 2.22 from the mean. Again, we have to preface it by reminding the reader that we are using many randomly selected sets of 20. So we're going to take many samples of 20. And then we're going to say that the number of successful free throws, that's my variable, will typically vary. Those are the magic words for standard deviation. Typically vary by about 2.22 from the mean. All of the underlined words are part of the rubric and critical to the interpretation. I'm going to give you here another problem. You're welcome to pause the video right here and work through this problem. It shows you how to solve the problem from beginning to end, including finding the probability, the average, and the standard deviation. So you're welcome to pause your video here, work through this example. I'm going to continue here by talking about the binomial probability distribution, particularly the shape of the binomial probability distribution. In general, you should know that the binary probability distribution is not bell-shaped. It is not bell-shaped, and as you can see from the top two graphs, it can be skewed. So in the upper left-hand corner, I have a low probability and a small n. And when I have that combination, my distribution is skewed to the right. On the upper right-hand corner, I have a large probability, maybe about probability of 0.8 or 0.9, and a small n. I have n equals 15. And in this scenario, the binomial distribution is skewed to the left. When the probability is 0.5, then we have an example. I have a drawing in the bottom left. That's an example where the probability is 0.5. When the probability is 0.5, the shape of the binomial distribution is symmetric. The probability is 0.5, the shape is symmetric. And if we get larger n and a p that is close to 0.5, then my distribution starts to look bell-shaped. And in fact, even if the probability is not exactly 0.5, as long as I have a large n, my distribution will be approximately bell-shaped. That becomes critical for our next chapter. Now, let me say a couple comments about the binomial distribution with large counts. As n gets large, the binomial distribution approximates the normal distribution. It doesn't equal the normal distribution, it becomes approximately equal to the normal distribution. And here's the rule of thumb that we are going to use. The binomial distribution approximates a normal distribution with mean equal to np and mu equal to the square root of n times p times 1 minus p, when n is so large that np is greater than 10 and n times 1 minus p is greater than 10. Sometimes we say that the number of successes is greater than 10 and the number of expected failures is greater than 10. This is referred to as the large count condition. And if the large count condition is satisfied, then the binomial distribution approximates a normal distribution. Don't say that it is exactly the normal distribution. It is approximately the normal distribution. You can read through these appendices, but I just wanted to leave you with this slide right here. The binomial probability for a range of values. Take a look at this slide right here. This is the notation that you can use if you're asked to calculate the binomial probability over a range. This is pretty handy, saves you lots of writing. That's it for today. Thank you very much.